4.1 Relations and Functions. Today, we're going to talk about what is a relation, and more importantly, what is a function? How are these similar? How are they different? So, let's start off with the definition of a relation. A relation, here I'm going to underline it, this is a set of ordered pairs of real numbers. Or you can imagine this as a set of points. The domain of a relation, here I use D to represent domain. This is a set of all x coordinates in my relation, whereas my range, denoted by an R, this is a set of all y coordinates in my relation. So, if you can think of whatever your favorite set of points are, then that would give us a relation. Since a relation is a set of ordered pairs, remember ordered pairs are points x comma y, my domain are all the x values, whereas my range is all the y values. And in particular, we know that relations can actually be represented in more than just points. We can imagine a relation as an equation, a graph, a set of points, or even a graph of points. There's many other ways that we might look at a relation. So let's go ahead and look at example 1. State the domain and range of this given relation. Here I have a set of points. My first point is 4, negative 6. My second point is negative 3, 2. And then I have 7, 5. So if I have a relation here, the domain, again we use D for domain, this is a set of all x values. So I'm simply going to go ahead and highlight all of my x values that I use here. In this case, my x values are 4, negative 3, and 7. One thing you're probably noticing is this sort of squiggly bracket I have. The set of squiggly brackets I have here denote that I have a set or a group. So here I have the domain, it's a set consisting of 4, negative 3, and 7. A couple of things I want to note about this before I go on to the range. The order does not matter. I could have put negative 3, 4, and 7, or maybe I want to put 7 first. Whenever I'm working in a set, the order does not matter. So now that we have the domain, let's go ahead and find the range of this relation. Well, the range of my relation should just be all the y values. And you've seen here, I've actually gone ahead and underlined all my y values. So for my range, I use my squiggly brackets to indicate a set. And now I put negative 6, 2, and 5, giving me my range. So again, my range is all my y values, whereas my domain is all of my x values. Note that in this case, we didn't have to encounter the situation, but if I ever have any repeating numbers, I don't need to write my repeating number multiple times. I just need to list out each unique value that I see. So to continue on this domain and range idea, let's go ahead and look at example 2. In example 2, this time I gave you a graph rather than a set of ordered pairs. Well, I can use a similar idea here. Remember, my domain is a set of all x values, while my range is all the y values. So in terms of a graph, all of my x values, that refers to how far left and right does my graph touch. Well, if I look at this graph here, on the far left, you might be tempted to say that we stop at this point. But this arrow actually indicates that my graph continues all the way. Just because I don't have that picture on my graph, it doesn't mean that it necessarily stops there. The arrow indicates that I continue in this direction. So this tells me that for this graph, it continues all the way left. In fact, all the way to negative infinity. On the right, my far right bound, I actually stop here at this point, which happens to be x is equal to 2. So my function goes from negative infinity to 2. And I want this as an interval. That is, I want to put my parentheses in my brackets if needed. Well, we remember that negative infinity always gets a parentheses no matter what. Whereas 2, if I look at my graph, notice that there's an open circle here rather than a closed solid dot. The open circle indicates that my graph is not actually defined at that point. That is, we are not including 2. So my domain is negative infinity to 2 with parentheses on the left and the right. Hence, we have our domain. Now, we can go ahead and look at the range. The range of my function is for all the y values. In other words, if I look at this graph, I'm wondering how far up and down do I go. Let's go ahead and start with my lower bound. Or in other words, the furthest down or the lowest point of my graph. Well, if I look at this graph, I can see the lowest point is what I've circled here. What y value does that correspond to? Well, that corresponds to a y value of -4. So my lower bound is -4. And then I need to figure out my upper bound. Well, if I look all the way to my highest point, again, you may be tempted to say this is my highest point that I've circled right here, but that's not actually my highest point. Again, I have that this graph goes all the way up. So if we look at this far left arrow, my graph goes upwards. It continues to grow in that direction. This arrow indicates that my upper bound should be all the way through infinity. And now I must put my parentheses or brackets as needed. Well, infinity always gets a parentheses no matter what. And in this case, -4, I'm going to put a bracket on -4. Because here my graph actually touches y is equal to 4. So I have the domain and range of a graph. So now we have some familiarity with what a relation is and the domain and range of that relation. Now we can move into our second portion. Remember, the section was called relations and functions. Let's go ahead and define what a function is. Formally speaking, a function is a relation in which each domain element x has exactly one corresponding element y. Or I can say each input x only has one output y. Or you can also say if I have a set of ordered pairs, each ordered pair has a unique x value. So let's go ahead and start with a basic relation in example 3. I have 3 relations here, and I want to figure out if these are functions or not. Remember what I said. If I have a set of ordered pairs, I am a function if all of my x values are unique. So I'm going to go ahead and focus on all of my x values. I'm going to go ahead and highlight them for each relation. Starting off with relation A, I have 2, 4, 5, and 6. Well, in this case, all of my x values, that is my domain elements, are unique. Since they are all unique, then yes, we are a function. Now we can continue to relation B. Here I have 2, 3, 4, and 5. Definitely all these are unique and different from each other. So I'll say yes as well. One thing I want to point out here for B is that my y values can be the same. That doesn't matter. I'm not worried about the y values being the same. I'm worried about my x values being the same. Now for relation C, I have 2, 3, 2, and 5. The first thing I'm noticing is I have a 2 here and a 2 in my third ordered pair. This tells me that my x values are not unique, hence I am not a function for part C or relation C. Thus, we are done with example 3 now. So if I give you a set of ordered pairs, you can tell me quite quickly if it's a function or not. However, we know that not every relation may be expressed as a set of points or ordered pairs. We know that a relation may be expressed as a graph. So that leaves the question, how do I know if a graph is a function or not? This brings us to the vertical line test. The vertical line test tells us if a graph represents a function or not. So what happens is that we take a vertical line that goes all the way up and down, and then we see, as I move the vertical line from left to right, how many times am I touching my graph? How many times are we intersecting? We want to make sure that my vertical line only touches my graph at most once per any given moment. If it touches my graph more than once at any given time, then we say we are not a function. So, looking at example 4, I have 2 graphs, and I want to see, am I a function or not? So on the left, again, I want you to imagine that we can draw a vertical line, and then we move it from left to right. Well, if I take this line and move it from left to right, we can see pretty quickly that my vertical line and my graph will only touch each other at most once at any given point. Hence, the graph on the left is, yes, a function. Now what about the one on the right? Again, if I have a vertical line, let's say we start on the far left. You might look at this and say, well, it's only touching my graph at one point. Is it a function? Well, this is where we have to be careful. The vertical line test says for every vertical line that we draw. So, for example, what if I had another vertical line over here? I can see that this vertical line is touching twice. If I have a vertical line touching my graph more than once, then we are not a function. Or in this case, the second graph, we know we are not a function, no. So this is a vertical line test. So now we're quite familiar about how to see if a relation is a function, regardless on if my relation is given as a set of ordered pairs or if it's given as a graph. Now that we're familiar with what is a function, let's introduce this new idea called function notation. We call function notation, we write it as this f of x. Again, we read this as f of x. This is called function notation. What this means whenever we write f of x, this means that I can write an expression that depends on a variable x. In other words, I might have something where it's f of x is equal to some expression that only involves x's and numbers. One thing I want to mention is that whenever I write this f of x notation, this is f of x. This is not f times x. Those mean two different things. The other thing I want to define is what does it mean to evaluate f of a? Whenever I say evaluate f of a, typically we're going to be putting a number in here. This means that anywhere there's an x in my function equation, I'm replacing it with that letter. You'll see what I mean a little bit whenever we start doing our examples. So let's look at example 5. If I have f of x is equal to 4x plus 3, evaluate the following expressions, simplifying as needed. So for the first one, I have f of 3. Remember what I said. F of 3 means I look at my original function, and anywhere that there is an x, I'm replacing it with that expression. In this case, I'm replacing x with a 3. So I can write this as 4 times, instead of x, I have 3 plus 3. This is me replacing my x with a different number or expression. Now my job is to clean this up. 4 times 3, I get 12 plus 3, giving me 15. So I have my final answer for f of 3. Now let's look at part B, f of x squared. So remember, this means that I look at my original equation, f of x is 4x plus 3, but I'm replacing my x with an x squared. What I often tell students is that whenever I have this f of x notation, if you want, you could rewrite this as f of some empty box equal to 4 times whatever's in that empty box plus 3. So in part A, I wanted f of 3, so I just filled in the blanks. That's how I figured out what f of 3 was. For part B, if I want to look at f of x squared, I'm just putting x squared into this empty blank. So f of x squared, this is 4 times x squared. I'm going to just use parentheses for now to be safe, which cleans up to be 4 times x squared plus 3. And there's nothing else we can do here to clean up. So I have my final answer for part B. We can do the same thing for part C. You might be looking at part C and saying, wow, this is a lot of letters. And there are a lot of letters, but we're still using the same idea. Once again, I'm going to go ahead and write down that blank box notation, where if I have f of some blank, this is equal to 4 times that blank spot plus 3. So if I want f of x plus h, that means I'm putting x plus h inside my blank. This gives me 4 times x plus h plus 3. And now I need to clean this up. To clean this up, I would go ahead and distribute my 4, giving me 4x plus 4h plus 3. Looking at this doesn't clean up or simplify anymore, so I have my final answer for f of x plus h. Thus, we are done with part C. The last part of example 5, part D, we have something that looks not that nice, honestly. It looks like f of x plus h minus f of x all over h. Well, we can actually break this down pretty nicely. If I look at this, f of x plus h, we know what this is. We found that in part C. That is, I know f of x plus h that is 4x plus 4h plus 3. Again, I'm going to use parentheses to be safe here. This is what we found out last time. Minus f of x. If I look all the way back to the beginning, we know what f of x is. We know f of x is 4x plus 3. Notice here that I'm putting it in parentheses because I do have to be careful about my minus. And this is all over h. Now my job is to clean this up. If I do some cleanup work, I have 4x plus 4h plus 3. And then I have to subtract 4x plus 3. Make sure you distribute your negative. This should give me minus 4x minus 3. And this is all over h. Continuing my cleanup work, here I have 4x minus 4x, and then I have 3 minus 3. This gives me 4h over h, which I can take one step further. Since h over h can cancel each other out, this gives me 4. And clearly 4 is a very clean number for us. So we are done with part D. I used what I knew from part C and my beginning information to fill in the blanks, and then I worked from there. So we're done with example 5. The last topic I want to cover in this video is something called the implied domain. The implied domain of a function is all the real numbers at which the function can be evaluated to obtain a real number. In other words, when I'm asking for the implied domain, we are working with a function equation, and I'm asking what numbers are you allowed to plug in such that I get a real answer. Well, whenever I'm looking at an equation, we have an infinite number of numbers that we can plug in. We have from negative infinity to infinity. Clearly, we're not going to try to plug in every single number possible. That would be impossible for us to work with. So instead, we like to work with what can we not plug in to get a real number. And remember, this means that I want to watch out for two things. Two things I know give me issues is I don't want to divide by 0. We know if I divide by 0, I get something undefined. And I don't want to take the square root of a negative number. We know how to take the square root of a negative number. We know that that would often give us an imaginary number. But we only want to talk about real numbers from now on. So let's go ahead and look at part A of example 6. Determine the implied domain of the function f of x is equal to negative x plus 3. If I go down to my two restrictions, again, I want to make sure that I don't accidentally divide by 0, and I don't want to take the square root of a negative number. Well, for part A, I don't even have a square root, and I'm not even dividing by an x. In other words, for part A, I'm not worried about either of those situations. Thus, I have no restrictions on part A. That means I can plug in whatever number I want, and I will get an answer. Or in other words, I can plug in all real numbers. Remember that this fancy R means all real numbers. Or you can just write out all real numbers. Or you might write negative infinity to infinity. All these are acceptable for us. Now let's look at part B. Here I have the square root of x minus 3 plus 2. Going into my list of restrictions, again, I don't want to divide by 0. I don't want to take the square root of a negative. Well, I'm never dividing by 0 in this situation. I don't even have fractions moving around. But I do have a square root. What I want is whatever's inside of my square root, in this case x minus 3, I want to make sure that that's not negative. Or in other words, I want to make sure that this is greater than or equal to 0. So again, I am setting whatever is inside of my square root greater than or equal to 0. This plus 2 in my function did not change anything at all. Now I'm going to solve for x. Here, if I add 3 to the left and to the right, I just say x is greater than or equal to 3, which, if we write in interval notation, is equivalent to 3 with a bracket to infinity with a parentheses, giving me my final answer. I have my implied domain. This means that if I plug in any number greater than 3 or equal to 3 into this function, I'm not going to run into any problems. If I plug in a number smaller than 3, for example, if I plugged a 0 into this original function, then I'm going to end up with some type of problem. Now, let's look at part C, our final example for this video. We have p of x is equal to 2x divided by 6 minus x. If I look at my restrictions, again, I don't have a square root, so I'm not worried about that. But am I worried about accidentally dividing by 0? Here I definitely have a fraction. What I'm going to do for this problem is I'm going to look at the denominator. I do not want this to be 0. That is, I want to make sure 6 minus x is not 0. If it is 0, then we have a problem. I'm dividing by 0. Now, let's solve for x. The quick way we can do this is to add x to the left and right, giving me x cannot be equal to 6. And you can check this. If I plug this in to this function, you would get divided by 0. We don't want that. So how do I write this in interval notation? Well, one way I can write this in interval notation is I can write it as negative infinity to 6 with 6 to infinity. And I'm going to go ahead and put a union symbol in the middle. Union for saying this interval with this interval. This is one way you might write it. Some people, or some textbooks, also write it in this set notation, where it's all the x's, where x is not equal to 6. So make sure you're just aware that there are multiple different ways that we might write the final answer, but in the end, our goal is saying, I don't want the number 6. And so that finishes our example 6 and our last one for this video.